Testing correlation. In this section, we are considering bivariate data, which we know we can represent on a scatter diagram like the one shown here. We can put on a line of best fit, which shows the trend of the data. We have previously discussed correlation, which is a measure of how related the two variables are. Visually, we can see that by how closely they fit to the line of best fit. The correlation coefficient is on a scale from -1 to 1. 1 would be a perfect correlation with a positive gradient like this. Every point is on the line. -1 would be a negative gradient with every point perfectly on the line. 0 is a cloud of points. This would be a positive correlation and a fairly strong one, so it might be about here on the scale. If the diagram represents the entire population, the correlation can be expressed as the population correlation coefficient, rho, which is a population parameter. Pearson's product moment correlation coefficient, PMCC, given the letter R usually, is a statistic which estimates rho from a sample. In all probability, R will differ from rho, but it should provide a better estimate as the size of the sample increases. We can carry out a hypothesis test for rho using calculations of R. When performing a hypothesis test, it is usual to define two hypotheses. H0 is the null hypothesis, which we need evidence to reject. If the evidence does not surface, we retain the null hypothesis. H1 is the alternative hypothesis. We accept this to be true if there is evidence to reject the null hypothesis. The null hypothesis for this test is usually that there is no correlation. So H0 normally takes the form that rho is equal to 0. H1 can take different forms depending on what we suspect. We might suspect that the correlation is positive, in which case H1 would be that rho is greater than 0. We might suspect that the correlation is negative, and therefore H1 would be that rho is less than 0. Or we might have that rho is not equal to 0 if we suspect there is a correlation, but we're unsure whether it will be positive or negative. So what would we consider as evidence to reject the null hypothesis? Usually we compute R and see if it lies in a critical region. So we know our correlation goes from -1 to 1. Let's say that 0.6 is a critical value. Then the critical region would be from 0.6 onwards. And if R lands in this region, then that would be considered evidence to reject the null hypothesis. So if R is greater than or equal to 0.6, assuming this is our critical region, we are in the critical region and reject H0. If not, we have no reason to reject H0. So if our value is not in the critical region, then we have to accept H0. Note, the figure of 0.6 was just an example. The critical region will change with factors such as the significance level of the test and the size of the sample. For H1 being rho is not 0, we would have a critical region at both ends. Another way of deciding whether to reject H0 is to use a p-value. So let's suppose once again that this is a critical region and we have a value here where we're testing at the 10% level, and this value corresponds to a 5% level. Then we would know that it's in the region. Let's just explain that just a tiny bit further. Using a p-value is just another way of deciding whether we are in the critical region. So I've got some values for critical values of Pearson's R, and these are for a two-tailed test, but it's pretty easy. If we look at this value here of 0.900 if you like, then for a two-tailed test it's 0.1, but if we were doing a 5% one-tailed test, that value would be used. So if you're doing a one-tailed test, you just halve the value here. Let's just consider this. This would actually correspond to having 12 in our sample, because the degrees of freedom for this test are the number in the sample take away 2. So you look at the line for 10 if you have a sample size of 12. If we were doing a one-tailed test with n equals 12 at the 10% level and found that R was equal to 0.497, that's got a probability of 0.05 for a one-tailed test. I just mentioned that. We just halve the 0.1 here. And then we have the situation in the diagram above.